Swayam Prabha. Digital India. Educated India.
This is going to be our last topic in this section on proof techniques. So, we will study an interesting thing today, which is called the pigeonhole principle. This is also often called Dirichlet's or just simply the box principle. Okay, same thing, box principle or Dirichlet's box principle. So, what is this? So, this principle goes like this. If m pigeons occupy n holes and m is greater than n, then there is a hole containing more than one pigeons. And in fact, I can give you a slightly generalized version of this. If m pigeons, exactly the same initial thing, occupy n holes, then there is a hole that contains at least ceiling of m by n pigeons. So I prove this general statement, although this is fairly straightforward. I prove this by contradiction. So I assume that all of these n holes contains less than these many pigeons. So each hole contains at most this -1 pigeons. And since there are n holes, total number of pigeons is less than equal to n times this. But now I use a property of the ceiling function, less than the ceiling of m by n cannot be bigger than this quantity. In fact, it's smaller than this quantity. M by n plus 1 and then -1, which is equal to m. So, if all holes contain less than these many pigeons, then the total number of pigeons is less than m, which is a direct contradiction, and therefore this theorem is valid. Okay, I mean the statements, often we take m equal to n plus 1 here or here. Then this says that there is a hole containing at least 2 pigeons. Here it says n plus 1 by n, n plus 1 by n, the ceiling of that is again 2. But this is the general set. Okay. Although the statement, these two statements and their proofs are obvious, this simple principle has far-reaching consequences. One thing is that the proofs that I will carry out using these results are usually non-constructive, because in this setting, given n pigeons and n holes, this setting or this setting, these theorems do not specify an algorithm to compute the hole which contains 2 or this many pigeons. Okay. It only guarantees that there must exist at least one such hole. Therefore, the proofs based upon this pigeonhole principle are usually non-constructive, only existential. Okay, but that doesn't matter. These are also valid proofs. Okay, so we will look at quite a few applications of this. One by one, let us look at some simpler things, and then we will proceed with a important application in number theory. As I mentioned in the last lecture, I will prove the Chinese remainder theorem. Anyway, let us start with simpler examples first. Okay, so example 1. So suppose that you are given an equilateral triangle. Okay. So this is an equilateral triangle, although the picture does not look like that. Each side is of length 1. Okay, then what you do, you pick some 5 points inside the triangle. So 5 points you take. Inside or on the boundary of the triangle. Now, the pigeonhole principle implies that no matter how you place these 5 points, you will always find 2 of these points at distance no more than half. Okay, this is n, no more than half. So basically these points are my pigeons, so I have to somehow create the holes. So what I do, I will break it down. This is half. Here to here, finally here to here. I will break the equilateral triangle into this 1, 2, 3, 4 parts. So these are my holes. Now, no matter how you position these 5 pigeons in these 4 holes, there will be at least one smaller equilateral triangle which will contain 2 points. And then it is easy to see that this length is half. If this total thing is 1, this length is half. Then you can easily see that these 2 points which go to the same smaller triangle must be at a distance less than equal to half. Okay. So this is a simple example. Let us move on to another example. Okay. Which one shall I take? Maybe. Okay, this one maybe. So consider this set S, which consists of the numbers 1, 2, 3 up to 12. And you pick something like n plus 1 numbers without repetition from S. Then you must have picked up two numbers A and B such that A divides B. B is a multiple of A. So, since there are n plus 1 numbers, so these are my pigeons, somehow I have to create n holes. Okay. So, in this case, the holes are like this. Consider this 1, 3, 5, 7, to n minus 1. So, there are n of them, odd numbers. Then we consider multiply by 2, 2 square and so on. This is my whole number 1. Of course, we multiply as long as you are within this range to n. Likewise, consider 3, 3 times 2, 3 times 2 square and so on until 5, 5 times 2, 5 times 2 square and so on. So these are not infinite sets. It will stop as soon as this 2n is exceeded. Okay. 7 times 2 square and so on. And this is definitely this. Okay. So this is my whole number 1, whole number 2, whole number 3, whole number 4 up to whole number n. And you have n plus 1 numbers. So you must have that 2 of these numbers will go to the same hole. Maybe here or here. But in that case, these two elements differ only by a power of 2. Therefore, one divides the other. Okay. So this is yet another simple example. Okay, let us come here. Example 3. Okay, so you are given n positive integers. A1, A2, up to an. So, there exists a non-empty subcollection of these numbers whose sum is divisible by n. Why? In order to prove this, you just consider these prefixes P0 equal to 0, P1 equal to A1, P2 equal to A2, A1 plus A2, P3 equal to A1 plus A2 plus A3, and so on. Pn equal to A1 plus A2 plus ... An. So you have this n plus 1 prefix sums. This is the empty sum. This is A1, A1 plus A2, A1 plus A2 plus A3, and so on. And if you divide these quantities by n, let us say you get these remainders R0, R1, R2, and so on, Rn. So Ri is Pi remainder n for all I. Okay. Now, modulo n, you can have at most n remainders, 0, 1, 2 up to n minus 1. And here you have n plus 1 remainders. So it must be that 2 of these remainders are repeated. Okay. There are even further repetitions, but at least one repetition you cannot avoid. So let us say this is Ri equal to Rj for some I less than j. Okay, but then what is Ri? I write it this way. Pi is dividing by n, so some Qin plus Ri, and Pj is Qjn plus Rj. If I subtract this from this and use the result that Ri is equal to Rj, we see that Pj minus Pi is a multiple of n. But what is Pj minus Pi? This is nothing but ai plus 1, ai plus 2 up to aj. Okay, so this is the non-empty subcollection. Because j is greater than I, this is non-empty, and they add up to some multiple of n. So that is my example 3. Okay, there are many other interesting examples. I take this one, example 4. So let m be an odd positive integer then there exists a positive integer n such that m divides 2 power n minus 1. Okay. So how do I prove this? Consider this. 2 powers n should be positive, so I should not start from 0, 2 power 1 minus 1, 2 power 2 minus 1, 2 power 3 minus 1, and to power n plus 1 minus 1. Okay. So as I did in the last class, in the last example, I divide all these things by m and consider these remainders R1, R2, R3, Rn plus 1. So, remainder of division, Euclidean division by m. So, if m are the remainders, there are m possible values 0, 1 up to m minus 1, that you have m plus 1 remainders. So, one remainder must repeat, right? So, once again assume that Ri equal to Rj for some I less than j. Okay. Then again, as in the last example, what is Ri? To power I minus 1 is actually why I am using minus 1s here. There is no reason. There is absolutely no reason, although there is no harm either. Just consider these numbers. 2 power 1, 2 power 2, 2 power 3. Although if you work with this minus 1, there is no problem. The proof is exactly the same. Let us take 2 power 1, 2 power 2, 2 power 3. Simpler things. So here also I remove this minus 1 and have 2 power I is equal to some qi m plus remainder is Ri, and 2 power j is qj m plus rj. Now I subtract. Of course, if I had minus 1 would cancel, but that's not necessary. What do I have? 2 power j minus 2 power I is equal to, if Ri is equal to Rj, I have qi minus qj m. And this side I rewrite as 2 power I, 2 power j minus I minus 1. So, this quantity, which is a multiple of m, is equal to this. Okay. But m is odd, and therefore it does not have any factor of 2. So, GCD of mn to power I must be 1. So, since m is a divisor of this quantity and no factor of m comes from this, it will come from this. So, m divides 2 power j minus 1 minus 1. So, that is my n. Yeah, this is my n. Okay. Okay, now let us do, I think, a numeric exercise. This one is interesting. Yes, sample 5. Maybe again I choose white. Example, this is 5th example. Okay, so suppose that you have got something like 40 assignments. and you want to solve in a period of 4 weeks, that is 28 days. So on each day, you solve at least one assignment. And you complete all the 40 assignments in 28 days. Okay. So do one assignment on the first day, 2 assignments on the second day, and so on. The assertion is, what we want to prove is that no matter how you schedule your assignments, of course, under this restriction, you solve at least one assignment on each day. No matter how you schedule your assignments, there must exist a set of consecutive days on which you solve 15 assignments. You cannot simply avoid this 15. No matter how you schedule your assignments. Okay. On each day you solve at least one assignment, of course. You either solve an assignment, not half of it or something like that. Okay. So let us say, so why? Once again, let us look at a proof of this. So let us say xi is the number of assignments solved from day 1 to day I. Okay. So x1 is equal to the number of assignments you solve on day 1. x2 is equal to the sum of the numbers of assignments you solve on day 1 and day 2, and so on. Then by the given conditions, you have this. x1, because you solve at least one assignment on each day, the sum increases. x1 less than x2 less than x3, and finally less than x28. Okay. Also, I define something. Maybe start a new page. For each I define yi equal to xi plus 15. Okay. So let us see. Let us go once more. So this is greater than equal to 1, and this is exactly equal to 40. Okay. So it is important to note this. Okay. Now I define the quantities yi equal to xi plus 15 just by adding 15 to each xi. Then I get again an increasing series, strictly increasing series, y1 less than y2 less than y3 and so on, y28, and this is greater than equal to 16. This is equal to 55. 40 plus 15 is 55. Now I consider to 56 numbers. x1 through x28 and y1 through y28. So there are 56 numbers, okay, together. So by the Pigeon principle, therefore, there must be a repetition, okay. But this repetition cannot happen among this xi's because it's a strictly increasing sequence. Likewise, the repetition cannot happen in the y series because it's again a strictly increasing sequence. So it must be that sum xi is equal to sum yj. But yj is nothing but xj plus 15. So this implies that xi minus xj equal to 15. Okay. That's it. Good. So that was our example 5. Okay. Now let us look at a final example, and then we will derive a number theoretic formula called the Chinese remainder theorem. Example 6. So we are given an array of n square plus 1 distinct numbers. Maybe all positive integers, doesn't matter. Then A contains either an increasing or a decreasing subsequence of length at least n plus 1. What is a subsequence? You pick some element of the array, then potentially skip some elements, take another array, another element, skip some elements, take another element, and so on. So this way you generate a subsequence. So this need not be contiguous. Okay. So how do I prove it? So, but whatever your array is, however unsorted or sorted it is, A will always contain either an increasing subsequence of length at least n plus 1 or a decreasing subsequence of length at least n plus 1. Why? Okay, so I assume that this is not the case and I will arrive at a contradiction. To that effect, I define two things first. Xi, the length of the longest subsequence ending at the ith element, ith array element. Increasing subsequence ending at the ith array element. Ending at means it must include the ith array element and then also some previous things, possibly, if possible. Okay. Likewise, I define yi to be the same thing, the length of the or a, whatever, need not be unique, so, but a longest decreasing subsequence ending at the ith array element. So that means I will include that ith array element, and if possible, I will collect some other elements from before the ith element. Okay. Then, what do I have? Then, once I have defined these things, I consider this pairs x1, y1, x2, y2, so on, up to x n square plus 1, y n square plus 1. So there are n square plus 1 such pairs. Okay. If this condition does not hold, then each xi is less than equal to n, each yi is also less than equal to n. Right? So if no increasing or decreasing subsequence of length n plus 1 or more can be found, it has to be, each xi has to be less than n plus 1, that is less than equal to n, and each yi should also be less than equal to n plus 1, less than equal to n. But every single element sequence is increasing or decreasing, therefore, this each xi is at least 1, each y is at least 1. Okay. So, if I assume that this condition does not hold, okay, if no increasing or decreasing subsequence of length n plus 1 or more, there are at most n square values of xi, yi, right? Xi can be anything between 1 to n, yi can be anything between 1 to n, so n square possibilities are there. But I have n square plus 1 such pairs. Therefore, there must be a repetition, that is xi, yi equal to xj, yj. Okay. Okay, so let us call ai is the ith array element. So now let us look at this thing. So this means xi equal to xj and yi equal to yj. Okay. And this is some sequence which ends at ai. This is also some sequence which ends at ai. Some sequence aj, ends at aj, ends at aj. And let's assume that j is greater than I. Okay. Now I told you that the numbers are distinct. So I have something like this. Let me have that array. This is my array ai. So this is position I. This stores ai. This is position aj. Okay, this is position I, position j. Okay. Okay, and I have xi equal to xj, yi equal to yj. Okay, so now the numbers are different. So there are only two possibilities, ai less than aj and ai greater than aj. Okay. Okay. If this condition holds, ai less than aj, okay, then you see that this is an increasing sequence. Xi's are lengths of increasing sequence. So from the beginning to this ith position, you have already found an increasing sequence ending here of length xi. And aj is greater than ai, so if I simply append that aj to that longest increasing sequence, I get an increasing sequence ending at aj and of size xi plus 1. So how can I have xi equal to xj? Likewise, if I have ai greater than aj, I look at this. Okay, so I already have a decreasing sequence of length yi ending at ai, and if ai is greater than aj, then I simply append that aj to that longest decreasing sequence, and I will get a decreasing sequence of length yi plus 1, that is yj plus 1, but why is it yj then? Okay, in both cases we see a contradiction, and therefore it is established that there must be at least one subsequence of length n plus 1. Okay. Okay. So this will be for the moment our final application of the pigeonhole principle. This is called the Chinese remainder theorem. Okay, so there are several variants of this theorem. I will prove a very simple one. Suppose that you are given two positive numbers m and n, and this is an important condition, they must be co-prime or relatively prime, so that this is 1. So I take a remainder r modulo m, that means r in the range 0, 1, 2 up to m minus 1, which is actually we have defined as Zm in the earlier class, Zm. Likewise, if I am given a remainder, let's say S, 0, 1, 2 up to n minus 1, we call this set Zm. Then Chinese remainder theorem says that, okay, there exists a unique integer x in the range 0, 1, 2 up to mn minus 1, such that when you divide x by m, take the remainder, it is equal to r, and when you divide x by, sorry, this is m. When you divide by n, you get the remainder s. Okay. Okay, so given any r and any s, you can club them together to some number x such that it's no bigger than mn, no bigger than mn minus 1, and when I divide x by m, I get this remainder r. When I divide x by n, I get this remainder s. Okay. So this is one form of the so-called Chinese remainder theorem. Okay. There are many other ways I can extend this. I can take multiple moduli m1, m2, mk, but anyway, let us not worry about this. Actually, given this result for two things, I can generalize for any finite number of moduli. So, how do I prove it? If I look at all the numbers in this 0, 1, 2 up to mn minus 1, that leaves a remainder of r modulo m. These are precisely r plus m, r plus 2m, and so on, r plus n minus 1 times m. Okay. So the maximum value of r is m minus 1. So mn minus 1 plus m minus 1. So it will be mn minus 1. And if you add another, if you consider mn plus r, it will be bigger than mn minus 1. So these are all the numbers in this range which leave a remainder of r when divided by m. So now I divide these numbers by n, the other thing. Okay, and let's say this remainder is S0, S1, S2 up to Sn minus 1. So Si is nothing but the remainder of R plus Im remainder n. Okay. So at least I have got n different n remainders modulo n, the second modulus. Okay. If any one of them is my given s, right, I have got n remainders. If any one of them is s, then I am done. So once again we proceed by contradiction. So I say that no Si is equal to S. So this is an assumption. If that is the case, then one possibility from this set is gone, right? So there are n possibilities and S never appears in that list. So one possibility is gone, so there are now n minus 1 remainders possible. Whereas I have n remainders. So there it must be that some remainder is repeated. Okay. So no Si is equal to S. So n minus 1 possible remainders. But I have n remainders. S0, S1 to Sn minus 1. Therefore, by the pigeonhole principle, I must have Si equal to Sj for some I and j satisfying this less than equal to I, less than j, less than equal to n minus 1. Right? So let us see how it leads to a contradiction. So Si is the remainder of R plus Im when divided by n. Sj is the remainder when R plus Jm is divided by n. And you also remember this inequality. 0 less than equal to I less than j less than equal to n minus 1. Okay. So, what do I have? R plus Im when divided by n, I get, this is I, this is I, this is Qin plus Si. Whereas R plus Jm is Qj, some quotient Qj n plus Sj. Okay. Now, since Si is equal to Sj, if I subtract the first equation from the second, I get R cancels, likewise Si, Sj cancel. Okay, then I get this, J minus I times M is equal to Qj minus Qi n. Right. Now, we are almost done. So, this side is a multiple of n, and therefore, because this is a multiple of n, this is equal to this expression also. This is also a multiple of n. Okay. So, n divides j minus I m. Now, I use the condition GCD m n equal to 1. So, n divides this, but has no common factor with m. So, it must be that n divides j minus I. But then, what do I have? I once again write 0 less than equal to I, less than j, less than equal to n minus 1. Then what will follow? J minus I is greater than 0 and less than equal to n minus 1. If that is the case, how can j minus I be a multiple of n? Okay, so this is a contradiction. Okay. So, there is no integer in the range 1 to n minus 1 which is a multiple of n. So, this is a contradiction which says that our assumption that no Si is equal to S is wrong. Okay, this does not hold. So, I must be able to find S somewhere in this and then we are done. Okay. So, only one thing that I still want to mention to complete this proof is, now I have proved that there exists an X. So, why is it unique? Okay. So, suppose that there exist two X and Y, each in the range 0, 1, 2 up to mn minus 1, such that X remainder m equal to Y remainder m is equal to R and X remainder n equal to Y remainder n equal to S. Okay. Now, so I can write X equal to something m plus R and something. Okay, so let me write. So X equal to Q. Okay, 1 m plus R. And Y is equal to Q2m plus R, and here x equal to q3n plus s, y equal to q4n plus s. Okay. Again subtract. You see that x minus y from this side it is this, from this side it is this, q3 minus q4 times n. Okay. So this says that x minus y, this quantity, is a multiple of m as well as a multiple of n. That is, it is a multiple of both m and n. And that is, it is a multiple of LCM m comma n. Okay. But m and n are given to be coprime. So their LCM is nothing but mn. So mn divides x minus y. So y must be of the form x plus some k mn. Okay. Now if k is not 0, then if I take any x in this range and I add mn to it, or subtract mn or 2mn or add 2mn or subtract 2mn, whatever I do, I go outside this range. So the only possibility is that I must have k equal to 0 and therefore y is equal to x. Okay. If k is non-zero, then even if one of these x and y are inside this range, the other one will go outside this range. Therefore, x and y are unique. X, or the solution, is unique modulo mn. Okay, so this is all I wanted to talk about as long as proof techniques are concerned. So let me stop at this point. I hope you have learned quite a few important things in this sequence of 7 lectures. Okay, so I will come back again later with a different topic, set sizes.